Hello and welcome to Lesson 17, our very last lesson for Unit 2 on derivatives. Today we are learning about higher order derivatives. So our learning goal is to determine and interpret second and higher order derivatives in the context of rate of change. So first of all, what is a higher order derivative? So you've already seen derivatives, and those are actually our first derivative. And sometimes you can find the derivative of a derivative and the derivative of that derivative and so on. And those will be your higher order derivatives. And specifically for our course, we do look at the second derivative quite a bit, and it has a big application, both when it comes to application questions as well as for our curve sketching unit. So we are going to get introduced to that today, and in our next unit, we're going to see some real-life applications of derivatives. So starting with our second order derivative as a definition, so considering the function y equals fx, if this has a first derivative y equals f prime of x, maybe not y there, it just has a first derivative of f prime of x, then we can say that the second derivative of y equals f of x is, again, I'll remove that for you there, is the derivative of f prime of x, so the first derivative, and it is written as f prime prime of x, so double prime there. And in Leibniz notation, it is written as follows. So we have the first derivative as dy by dx, and we're just taking the derivative of that with respect to x. So again, d of this derivative by dx. And in notation, this part is very important, so please don't forget this when it comes to the notation for Leibniz notation. You do have a exponent of 2 there, but in the numerator, it is belonging to d because we're saying the second derivative of y with respect to x, and then we see the 2 now here for x because we're saying with respect to x twice. So now let's see some examples of what that might look like. So I have 3 examples here, and we're going to see how all the properties of derivatives that we've learned so far are going to be applied here. So consider our first function, f of x is 4x to the power of 7. So we know that the first derivative is equal to f prime of x, which is 28x6. And the way we get that is we consider 4 dx7 by dx, and taking this 4 out is our constant multiple rule of derivatives, and now I just have the power rule, which tells me f as a coefficient and then x to the power of 6. And that 7 and 4 become 28, and we're left with x to the power of 6. Now, taking the derivative of this one is very similar. So we're finding the second derivative here. We are now doing d of 28x to the power of 6 by dx. And now here we have 128. This is just 6 times 28, and our power is x to the power of 5. Just decrease it. So as you can see, the derivative rules apply the same way. It is just that now the function that we are finding the derivative for is itself a derivative. But again, that doesn't change the way that we apply the rules. Now for the second example, we have x squared plus 3 in bracket, and this is raised to the power of 5. So we have our chain rule here because this is a composite function. So applying the chain rule to find the first derivative, we have 5, which is our exponent. X squared plus 3 remains the same, and now our exponent here has decreased to 4. And then the derivative of x squared plus 3 is just 2x, because here we have the power rule and 3 is just a constant. And this can just be simplified to 10x times x squared plus 3 to the power of 4. Now, to find the derivative of this, as you can see, this is 10x times x squared plus 3 to the power of 4, and this is the product rule. And so applying the product rule, remember we take the derivative of the first function times the second function plus the derivative of the second function times the first function. And that's exactly what I've done here. So 10 is the derivative of 10x because if you remember, dx by dx is just 1. And then I just have x squared plus 3 to the power of 4. And now for this part, I'm taking the derivative of x squared plus 3 to the power of 4. So I have that coefficient of 4 and x squared plus 3 to the power of 3. Don't forget here that we still have a chain rule within that. So we have that 2x again because now we're finding the derivative again. So it's still like we treat it as a new function and we applied the chain rule. And then my 10x, which is my first function. And here now you can see that x squared plus 3 cubed is a common factor in both of these. And so I can factor that out. And then I have my remaining terms. And I want to pretty much simplify these so I have a nicer expression for my second derivative. So here I've just done the distributive property, and this one we can evaluate as well. We'll just have 80x squared. Um, so 80x squared. And now this whole bracket is also 90x squared plus 30. And so I just factored out that 30 in there as well, just again for making it look nicer and it's a more simplified term. And we are left with 30 times x squared plus 3 to the power of 3 or cubed, which was this factor here. And then I am left with 3x squared plus 1. And that would be our second derivative of x squared plus 3 to the power of 5. Now for the last one, we have y equals the square root of 2u plus 1. So we're going to apply for the chain rule here because we have 2u plus 1, and this outer function is our square root function. So here, and remember, square root is just power of 1 over 2. So let me just maybe rewrite that. 2u minus 1. This is 2u, oh, plus 1. Plus 1 to the power of half. So now, applying the power rule first, I have that half there, and then 2u plus 1 is just 2u plus 1. And now my exponent is half minus 1, which is negative half. And this is actually now, oh, oops, 2u plus 1, negative half. This is 1 over square root of 2u plus 1. But you don't need to rewrite it as that. You can just keep it as the negative exponent. It will be fine here. And then the 2 is just the derivative of 2u plus 1. And then the 2 and the half just simplify to 1, and I'm left with 2u plus 1 to the power of 1 over 2. And this part, I just wanted to bring attention to here as well. Notice here that we are differentiating with respect to u. So when your input variable is anything other than x, and we're not doing a change of variable here, that's just a variable that we were given, then we are actually finding the derivative with respect to the variable that we were given, which is u. So dy by du. And now we find the second derivative here. So again, pay attention, it's d squared y by du squared. And this is just the derivative of this, which, as you can see, this is very similar to our original function. It's just the exponent is now negative, so same process. We have the power rule give us the negative 1 over 2, and our exponent is now negative 1 over 2 minus 1, which is negative 3 over 2. And then the 2 again is just the derivative of 2u plus 1. And the 2 and the 1 over 2 are canceled out. They simplify again. But this time we have a negative. So -1 and oh, this should be a 2. This time I did rewrite it for you as the fraction, so I just wanted a positive exponent. So when you have a negative exponent, it is better to like sometimes write it as a fraction, so you end up with a positive exponent. But again, for the sake of right now, either way is okay. And that's how we find the second derivative. Now, let's bring some application into this because you might be thinking, okay, I know the first derivative, and you may have you may have an understanding of the applications of that now, but now we introduce the second derivative. So what's the purpose? And specifically consider displacement, velocity, and acceleration. So some definitions to start us off. Position, which is usually denoted by the variable s, is the displacement of an object relative to the origin as a function of time. So, for example, if we are saying s of 2, we are saying what the position of an object is after 2 units of time. And that could be hours, seconds, minutes. So let's say after 2 hours, what is the new position? And with respect to where we started from. So if you started, for example, at 0, now we're saying, have we moved like 10 meters? And now we're at a distance of 10. Um, Now, velocity is the rate of change of displacement with respect to t, because again, that's our input variable. So maybe let me write that here. So this is really s of t as a function. And then this one would be v of t. And so velocity is actually also the derivative of the displacement function s, because we're pretty much saying, so you've moved from one position to another position over this amount of time. And now the derivative is telling us what our rate of changes at any given time. So at that 2 hour mark or whatever um, time that we're looking at, what is the rate of change in that moment? So how fast are we moving? And so considering now that v of t is the derivative of displacement function, then we have that v is equal to ds by dt, so the derivative of the position function or displacement function, or vt, which is our function notation, is s prime of t. And now we have acceleration. Now, acceleration is the rate of change of the velocity. So, for example, you are speeding up and you keep speeding up, and we want to know what the rate of change of that speeding up is with respect to time as well. And so acceleration being the derivative of the velocity function v, that is actually also a second derivative to the displacement function because it's a derivative of a derivative. And so how we denote that, so acceleration is going to have the a notation, and this is dv by dt, but dv by dt from the definition up here is in itself a derivative, so we technically have d squared s by dt squared because our original function here was s. And in function notation, we say that a t, so acceleration at time, is equal to v prime of t. So the derivative of the velocity, or s double prime of t, which is the second derivative of the displacement. Now, let's look at this table here, which is giving us some observations about velocity and acceleration. And one thing as well I want to point out here, and I did mention it in one of our previous lessons, but now we're looking also at direction. So speed in itself is just a distance, the change in distance over the change in time. But velocity is giving us direction. So for example, if I am moving east and that's my, so I started at a certain time and I'm moving east. If I keep moving in that distance, or sorry, in that direction, then I am moving at a positive velocity because I'm going in that same um, direction. But if I now am switching directions, then or like now I'm going west. Now that is a negative velocity because I'm going in the opposite direction. So we have now the direction piece in there as well as the speed itself. So for example, positive velocity is going to be when v of t is greater than 0. And this means the object is moving in a positive direction. So that could be, and usually we associate right, moving right, or moving up with a positive direction. So in examples of a rocket being, or a rocket going into the sky, or like a ball being thrown up, it is always that up motion that's positive for us. Now, a negative velocity, which is vt less than 0, is when an object moves in a negative direction. And again, that's left or down. Zero velocity, when v is equal to t, is pretty much when the object is not moving, so it is stationary, or when it changes direction. And consider even like thinking with real life application, whenever you want to change the direction that you're moving in, so imagine you're walking and you want to now switch to the other side. There is a moment where you turn to the other direction to go to the other, start walking in the other direction or start moving in the other direction. And that itself is in very, like, our instantaneous rate of change in that moment is 0. So we're not, we would say that we have a zero velocity in that moment of change. Now let's look at acceleration. So we can have also positive, negative, and zero acceleration. When we have a positive acceleration, so at is greater than 0, that means our velocity is increasing. So we are traveling in a positive direction and we are also speeding up. Um, Now, similarly, when acceleration is less than 0, we say that our velocity is decreasing, and in so we are speeding down, and in this case, we're also still traveling in a positive direction. Now, we can also have a zero acceleration, which is our velocity is constant, which means that you're just moving at the same constant speed. And so you're not speeding up, you're not slowing down, and you're still just moving in that direction. Now, here's just putting that together, speeding up and slowing down. So if your acceleration and velocity are, when you multiply them, it is greater than 0, which means they are either both positive or they are both negative. Then we say that we are speeding up. So consider that you're moving in a direction and in like you're moving to the right and you're speeding up, and your velocity is increasing, as well as your acceleration is increasing, then we can say that we are speeding up in the same direction. But consider now that when you multiply them, um, the product is negative. So one of them is they're opposite signs. So one could be positive and the other is negative. And in that case, we say we are slowing down. So if you are, for example, moving in your positive direction, but now your velocity is decreasing, that means that now you are slowing down. Alternatively, if you're moving in the opposite direction, but your velocity is increasing, then we can also say that you are slowing down. Now, I want you to think of some real world examples, like other than the ones maybe mentioned just now. Consider maybe movements of rockets, cars, any moving object, and how we might be able to apply some interpretations from this table to those examples. So now we are looking at some graphs that are position versus time. So our position and time graphs, and we're going to apply those interpretations of velocity and acceleration over here. So in our first example, this is a linear line, and I'm just going to label our graphs. This is position, and this is time. So in this example, we have um, our displacement is increasing at a constant rate, which means that you're moving at the same amount of, for example, the same amount of meters in the same amount of time. So if you're moving 5 meters in 1 minute, you're doing that at every 5 minute interval, or sorry, at every 1 minute interval. And in this case, we can say that S clearly we see that S of t is increasing. Here, B of t is it's positive, and it's actually also going to be a constant. And think of when we did first differences in back in grade 9 when we were looking at linear functions, that's pretty much what that is. It's that rate of change, and it is constant here, and as well it is positive. And we can also have this something like this. And in this case, we would have it a constant velocity, but it would now be negative. So it might be like -5. And finally, our acceleration here is also 0. And I did put this up here just as a reminder that v of t is s prime of t and acceleration is s double prime of t, so the second derivative of the displacement. Now, in this second example, we can see that our function is increasing. So we are moving in a positive direction. But as we are increasing, we see that the curve is going towards a straighter line. And so in this case, we have uh, our velocity is positive, and decreasing. Now here we're going to start bringing those tangents back in because it's really going to help with visualizing this. So here, consider the tangent here. Okay, consider that. And then consider the tangent perhaps at this point. Now, these are actually s prime of t, right? And the slope of them is s prime of t. But this is also equal to v of t. So we can see here that v of t is positive, which means that it's greater than the values are greater than 0. These are positive slopes. But you can clearly see that this slope is greater than this slope. So over time, the velocity is actually decreasing, which then means that we are slowing down. So our acceleration is negative. Now, and now if we go back to this table here, we can clearly see that we have this example here where our velocity is positive, but our acceleration is negative, so we are slowing down. And consider acceleration is also the rate of change of these slopes. And clearly we can see that from, for example, this slope to this slope, it is decreasing. So that's why we also have acceleration is less than 0. Now, in this next example, we're also going to visualize with those tangents. So let's consider this tangent here and this one here. And now we see that the tangents here, so the slopes, which are v of t, they are actually negative slopes. And it's just, we can clearly see that just from the shape of them, they are negative. And now the slope here compared to the slope here, we are now increasing. So that means our acceleration here is actually um, acceleration here is also negative. And the reason for that is while we have a negative slope, the slope here is getting more and more negative. So this might be negative 3, and this might be negative uh, 15, for example. And so, in fact, and let's make a connection here. If we multiply them, we have this case where they're both negative, so we are speeding up. And we can actually see that that is true. We are speeding up here, just in the opposite direction. So that we get from our velocity being less than 0 as well. Now, in the next example, we have our displacement is also negative. We're going towards the negative on our y-axis. But here, let's look at those tangents again. We do have those velocities as 0, those tangents are 0, but we can see that they are actually becoming more and more positive. So the rate of change here, which is our acceleration, is actually positive. And in this case, though we are moving in the opposite direction because of v of t less than 0, if we go back here, when you multiply them, it is less than 0, and we can see that we are slowing down. And finally, in our last example here, we have that the displacement clearly we're increasing, and you can see that it is actually getting faster here. And so here we have v of t is positive. And if we draw those tangents again, we see that now they are becoming more and more positive. So a of t is also greater than 0 here. And then we have our final example where if you multiply them, the product is positive, so we are speeding up here as well. And you can clearly see the 4 cases of our position and time graphs with respect to velocity and displacement. Now let's look at an example here. We are considering an object that is moving along a straight line. So its position s of t to the right of a fixed point is given by this graph. So that means our positive direction is to the right. And we're asked, when is the object moving to the right or left? So now we first have to see which parts of the graph are increasing, which are going to be when we are moving to the right, and the parts that are decreasing, we're moving the opposite direction, so we are moving left. So considering here, I am moving up, and so from t0 to t2, I have an increasing function, so that means I'm moving to the right. And now here, I maybe turn around, and now I'm moving to the opposite direction. And so from T2 to T6, we are moving to the left. And finally here, we see that it is going back up. So, and that's the data that we're given. So we go based off of that. And now notation-wise, we say that we have S of t increasing for time 0 to t, between 0 and 2, and for t greater than 6. And for when we are moving to the left, we have the interval between 2 and 6. So t is between 2 and 6. So in that case, the value of S of t is decreasing. So we know that our object is moving to the left. Now you might be thinking, what about t2 and t is equal to 6? Why are these not inclusive equalities? And that has to do with our next question, which is, when is the object at rest? And consider those tangents that we would be drawing for any of these points, and consider at point T2 and at point T6. We actually have at these times v of t is equal to 0. And again, this was s prime of t. And so at time equals 2 and time equals 6, we say that because we have that change in the direction of the motion, then the object is momentarily at rest. And keep in mind, the derivative was instantaneous rate of change anyway, so it's very small and brief moment, but nonetheless, we do have that the object is at rest for that slight moment when we are changing direction. Okay, now for our next lesson, we are told that the position of an object moving on a line is given by the function s of t equal to 4t squared minus t cubed. And t is greater than or equal to 0, keeping in mind that t is time, so we're often going to see that with time. And so s is also in meters here, and t is in seconds. So we're asked first, is the object moving in a positive or negative direction at t equals 2 seconds? So to find that, we're going to find the velocity. So v of t, which is equal to s prime of t, our derivative, is, and I'm just using the power rules and the sum rule, or the difference rule here because it's a negative. So here we get 8t from 4t squared, and t cubed is just 3t squared. Then at t equals 2, v2, which is also equal to s prime of 2, is going to be equal to 8 times 2 minus 3, 2 squared. So we have 16 minus 12, which is 4. And so this is a positive velocity. And so we have that the object is moving in a positive direction. And keep in mind here, one thing we could do, for example, is to find s of 1 and s of 2. So s of 1 would give me 4 minus 1 is 3, and s2 would give me 4 minus 8, which is 8. And I'm now seeing that my displacement is moving from 3 to 8, and so I am actually moving up. So that is also another way that you could have interpreted this as we are moving in a positive direction. That being said, this is asking for whether we are moving in a positive or negative direction at a specific time. And that's why it's better to work with velocity, because velocity is our derivative, which is the instantaneous rate of change. And at a specific time, really what we want is the instantaneous rate of change, not necessarily the average rate of change, which is what we might see when we compare it like this. But it still is great to make that connection here as well. Now, for the second question, we're asked, is the object moving in a positive or negative direction at t equals 3 seconds? So same thing, but now we're just using t equals 3. And now I already have my derivative from up there. And again, this is s prime of t. So we have 8 times 3 minus 3, 3 squared. So then we have 24 minus 27, which is equal to negative 3. And now this is actually a negative velocity, and so the object is moving in a negative direction. And we can assume that for some time between t equals 2 and t equals 3, we had a change in direction, and so that's why now we are moving in a negative direction. And if we are looking at the graph, and this is 2 and 3, we might have something like, and then you start, and this would be like a point between 2 and 3, and this is also the point where v of t would be equal to 0. Now, we're also asked for part C to find the acceleration at time is 3 and use that to determine if the object is speeding up or slowing down. So here, we first have to find a of t, and a of t is v prime of t. And this is also s double prime of t. So the second derivative of this displacement function. But since we already had v of t from up here, then all I'm doing is finding the derivative of 8t minus 3t squared. And that was actually pretty simple. We just have 8 minus 6t. The 6 comes from the 3 and the 2. And at time 3, a 3 is negative 10. Now, this isn't our answer right away. We have to remember that table, and because v of 3 is negative 3 and it's less than 0, and a of 3 is also negative, so it's less than 0, then when you multiply them, you have a positive sign, and that actually means that we are speeding up. So don't be confused by just the fact that this is negative, that that means we are slowing down. We have to compare the velocity and the acceleration. And so in this case, we are moving in the negative direction, but we are speeding up as we are moving in that negative direction. So we are ultimately speeding up there. And so we can say that our tangents are getting more and more negative, perhaps. Now, one last thing we're going to look at for this lesson is the concept of extreme values. So we are going to have a lesson on this later on. That's why we have lesson 27 right there. We're going to see it when we work with our curve sketching unit, but it will be very useful to have a comprehension of it as of right now, because we are getting prepared for unit 3, where we're going to look at applications of derivatives, and it's important to consider those minimum and maximum values. So a maximum value of a function that has and we have to have that the derivative exists for these functions. So specifically, we look at intervals. So it may not be the derivative might not be defined for a function for the whole function, but we look at it for a specific interval. And if the derivative is defined at all of those points, then we can try to find the maximum. And the maximum will be the it could be at one of the peaks. So, for example, if we have something like this would be our maximum point. And as you can make connections now, at this point, we have that, and let this be point x is c, then we can say that f prime of c is equal to 0, which means that tangent is 0. And think of that as that our change of direction point, or a turning point. So here we have the derivative 0, and this could be at the peak, or it could be at an endpoint of the interval. And soon I'm going to show you a graphs of what that might look like. Now, similarly, the minimum could be the lowest point, so a valley, and we could have this point x is c. And again, similar to above the one before, f prime of c here is 0 because we have that turning point or change of directions, but just our curve is upwards now instead of downwards like the other one. And we can also have a minimum also at an end point of an interval too. So in any given interval, we compare the turning points, which are the points where the derivative is equal to 0, as well as the endpoints to be able to determine when we have a maximum or minimum. So before I show you the algorithm for how we do that, I'm just going to show you the graphs for what that might look like and why we have to consider the endpoints as well. So for example, in this function here, we have that maximum, we have that minimum, and we compare our endpoints, and we do see that this is actually our true maximum on this interval, and this is our minimum. However, in this example, you have a turning point here and a turning point here. And although this is our maximum in relative to all the points here, our minimum is actually not this valley here, because your endpoint is lower than this minimum here. Now, that being said, we do not necessarily have a tangent here, and that goes because of our left-hand side and right-hand side limits. We can't necessarily define the derivative at that point because it is not defined in our domain. So we don't necessarily have that f prime here is equal to 0, but it is still our minimum. And that's why you have to consider those endpoints, because sometimes the derivative won't actually give you the true minimum or maximum. And same thing here. Now, but we have in this example, both the minimum and maximum are at the endpoints. And again, because of those turning points, we have those values for f prime of c here, for example, 0, but we have points that have a higher output value and a lower output value than those turning points, and those are our true maximum and minimums, and they happen at the endpoints. So, putting that together now, if a function has a derivative at each point on the closed interval x between a and b inclusive, then First, we calculate all the points where f prime of x is equal to 0, and those again are our turning points. And then we find the output value for those points, as well as the endpoints equals a and x equals b. And we can finally conclude that the absolute maximum value on a closed interval, and the closed interval is also shown as the square brackets a and b because of the inclusivity. And the absolute maximum value is the largest of these values, and the absolute minimum value is the low or the smallest or lowest of these values on that interval, which again could be the endpoint or it could be one of the peaks or the valleys. But you have to find what f of x is at each of those points in order to make your conclusion. And that's a wrap on our lesson as well as Unit 2. So I hope you learned a lot about derivatives. You do have a discussion post just to wrap up your learning from this unit as well as to make connections to real life applications. And your next lesson is the summative for Unit 2. So best of luck on that. And as always, if you have any questions, don't hesitate to reach out and I'll see you all in the next unit.